You guys home so you can start pre-partying for the Raptors tonight.
It's raining over there.
We should have had the lecture in Jurassic Park this morning, just so we could start queuing.
You think they'll win today?
No.
Why not?
That's what I've said in every game. Like, I believe they're going to win.
But that's why.
They keep winning.
I'll maintain that they're not going to win, and hopefully they will win.
I mean, they were losing the last game at the beginning.
I stopped watching when they were losing. When they came back to watch, I'm like, oh, they're winning. Oh, we came back to finish it.
All right, so today we're going to talk about the hospital method,
Imagine losing to win.
or
That's how hard.
L'Hôpital's rule.
Oh, God. I've been cheating and using this.
And this is a strategy
I literally hate
for taking limits of indeterminate forms. Yeah, I heard it out there, and you are correct. All right, so first we have to discuss what indeterminate forms are. So what are the indeterminate forms? Well, these are basically like sort of nonsense numbers. Right, so the following, so how can I define this? I'm going to call it indeterminate form, an IF is a meaningless expression like, and who remembers some of the indeterminate forms? Yes, sir.
0 over 0.
Yeah, 0 over 0, infinity over infinity, infinity minus infinity, 0 to the power of 0, although that really depends how you define the exponent. And actually, this one I found surprising. 1 to the power of infinity is also an indeterminate form. All right, so here's the theorem, and I'll write it, and then we'll just do a bunch of examples. L'Hôpital's rule. Okay, so when you have f of a and g of a, when you have their quotient is equal to 0 over 0 or infinity over infinity, we know that the limit of x goes to a of f of x over g of x is equal to the limit of x goes to a of the derivative of f over the derivative of g. Now, you have to be very careful here. I'm not saying that we're going to apply quotient rule. We're not applying quotient rule. All right, this is really taking the derivative of the top and taking the derivative of the bottom, like separately, as functions themselves. And of course, this is assuming right-hand side exists. Right, our theorems usually just assume everything is going to work out. So I'm not going to give you those details because we'll leave that to the real analysis people. Okay, so here's a simple example. What is the limit as x goes to 0 of 3x minus sine x over x? Okay, so the first thing you should do in any limit is always try to evaluate the limit, right? So if I put 0 into here, what do I get? That's 3 times 0, that's 0, minus sine of 0, which is 0, over 0. Right, so this really has the form 0 over 0. Okay, so I'm going to show you a little piece of notation that will help you stay organized when you're doing these things. If you want to apply L'Hôpital's rule when it is appropriate, you indicate that you've done so by writing an h over the equal sign. Right, so I'm saying this limit is equal to, by applying L'Hôpital's rule to the following limit. The derivative of the top here is 3 minus cos x. The derivative of the bottom is 1. And now if I put in these values, you get 3 minus cos of 0, which is 3 minus 1, which is 2 over 1. So this limit actually ends up working out to 2. That was, what am I doing? Geez, I really borked something in here. But in any case, I think I combined two. So my notes are like truly broken. I think I combined two limits into one. Okay, well that still works, technically. Let's try another one. Let's do limit x goes to 0 of x minus sine x over x cubed. So let's first confirm that we can use L'Hopital's rule. So we get 0 minus 0 over 0. This is very similar to this one. So I'm going to apply L'Hopital's rule. You get limit of as x goes to 0 of 1 minus cos of x over 3x squared. Now, what do you see here? What happens if I put x equals 0 into this? What do you get? So this was 0 over 0. What is this? So this is 1 minus cos of 0, which is 1. That's 0 over 0. So what do you think we do? Yeah. So this is an example. This is to demonstrate that you may have to use the rule multiple times before actually converging on something that's going to give you a non-indeterminate form. So again, I say I'm going to use L'Hopital's rule once more. We're going to get limit of x goes to 0 of 0 minus the derivative of this. So you get a plus sine of x over 6 of x. Well, I still get 0 over 0. So we can use it again. And you're going to get limit x goes to 0 of cos of x over 6, which is going to be equal to a sixth. All right, so we had to apply L'Hopital's rule 1, 2, 3 times in order to get rid of the 0 that was dividing through the bottom. So it shouldn't be a surprise that there is a cube there. Okay, I want you to give this one a try while I wipe the board. What is the limit of x goes to 0 of 1 minus cos of x over x plus x squared? Give that a go. All right, what do you guys calculate? Anyone get an answer? Well, I got 0, so let's check this out. So let's try evaluating x into here. You get 1 minus cos of 0. Cos of 0 is 1. That's going to be 0 over x plus x squared, which is 0. So we can use L'Hopital's rule here. So you get limit of x goes to 0 of the derivative of the top. That's 0 plus sine of x over the bottom, which is 1 plus 2 of x. Now, don't be tempted to keep using L'Hopital's rule. At this point, you have 0 plus sine of 0. That's 0 over 1 plus 0. So actually, this just works out to 0 over 1, which is 0. All right, so stop using L'Hopital's rule. You can only use it when you have the indeterminate form 0 over 0 or infinity over infinity. All right, so let's look at forms involving infinity. So when we have forms involving infinity or limit calculations in general, remember, we can always manipulate the limit a little bit in order to get it to look like something that's more easy to compute. As long as we're not like, well, we're allowed to do things like multiply by 1 or divide by stuff. So here's an example. Let's look at the limit as x goes to infinity of x times sine 1 over x. So what do we get if we put infinity into here? We're going to get infinity times sine of 1 over infinity, which is 0. Sine of 0 is 0. So you get infinity times 0, which is an indeterminate form, but not an indeterminate form that L'Hopital's rule can actually apply on. Right? So this is an indication that you're not going to get a limit without manipulating this. Right? But this is not allow you to use L'Hopital's rule, so be careful. The only two cases are 0 over 0 and infinity over infinity. And somehow those are that's basically the same case. So how can we manipulate this a little bit to get the form that we want? Well, I'm going to show you a little trick. We're going to swap out x to infinity for something else. If I say let x equal to 1 over h, and then I take h to 0 from the right, notice x goes to positive infinity. All right, makes sense? If I swap this out, if I take h to 0 from the right, this is going to go to positive infinity. So I can replace this limit with this one. Limit h goes to 0 from the right of x, so that's going to be 1 over h. I'll write it like this. Of sine 1 over x, so that's going to end up being sine of h. So what do we have here? We have sine of 0 from the right, that's 0. And then h from the right is also 0. So now we do have 0 over 0, the indeterminate form. So now we can use L'Hopital's rule. So we take the derivative of the top and the bottom. So we get limit h goes to 0 from the right of cos of h over 1. So if we put 0 in now, what do we get? We get cos of 0, which is 1. You get 1 over 1, which is 1. All right, let's do another one. Let's look at limit x goes to 0 from the right of root x ln x. So what indeterminate form is this? So if I put x to 0 from the right, this goes to 0. And then we multiply by what's 0 from the right of ln x? All right, we should always have the pictures of these standard plots in the back of our mind. This is ln of x. Right? Remember that it's the reflection of e to the x. You should remember how to do e to the x, because e is just the number. And so every number, every exponential function looks like this. And then you just get the reflection to get ln of x. So given that I've just drawn you ln of x, what's the limits of ln of x as x approaches 0 from the right? Okay, we agreed once when I was teaching you about limits that if I gave you the graph, you should be able to read the limit. No problem. Yes, sir?
Does it cross 0?
Oh, well, no. I just drew this like a not well.
So it never reaches 0.
Well, 0's here. Limit. We're asking where, you're giving me x. We need to talk about y. Yes, miss? Negative infinity, right? If I look at this graph and I go this way, you're going to head to negative infinity. We got to be sort of more comfortable with these limits now because I'm going to use them flippantly. Right, so please be comfortable with that. So you've got 0 times minus infinity. So that's an indeterminate form, but not one that is appropriate for use with L'Hopital's rule. So we got to do a little bit of fiddling with this. So I'm going to show you how to do something, and you tell me if this has made you uncomfortable. I'm going to take this x, and I'm going to put it on the bottom. But I'm going to put it on the bottom as 1, over the square root of x. Do you see how these two things are equivalent? Yeah? Right, just note that if you have a over 1 over b, this is equal to a times b. All right, so that's all I did. All I did was go from here to these are exactly the same. Arithmetically, they're equivalent. Okay. Okay, but now what do we have? The top goes to minus infinity. What does the bottom go to? 1 over 0 from the right, which is infinity. So you get minus infinity over infinity. We don't really care about the minus because we can always take the signs out of the limits. Whoops. That definitely shouldn't be there. Because I didn't actually apply L'Hopital's rule. Now we can apply L'Hopital's rule. So what's the derivative of the top? What's the derivative of ln x? 1 over x. And what's the derivative of 1 over the square root of x? Well, this you could really think about as being x to the power of the negative 1/2. So if I take the derivative of x to the power of negative 1/2, you get minus 1/2 x to the minus 3/2 down there. All right, so now we have to reorganize things a bit. We're going to get limit x goes to 0 from the right of, okay, so let's do this carefully. We're going to get a minus. This 2 is going to come up to the numerator. So we have a minus 2. What else is going to come to the numerator? This guy will come to the numerator because it has a negative exponent. So we're going to get an x to the 3/2 up here. And then we're dividing by x. Okay, so if I simplify a bit, you get limit of x goes to 0 from the right of minus 2x to the 1/2. Hope I did this right. Seems like I did. And then from this, you get 0. All right. Let me give you an example or an exercise while I wipe the board. So give that one a try. Let me see here. Limit x goes to 0 of 1 over sine of x minus 1 over x. See if you can do that one. One lap. What did you try?
We multiply each term by it.
Why don't you try making one back?
You could. Can you do L'Hopital's before? And why not?
Oh, thanks.
No, but 1 over 0 equals infinity. And then 1 over 0 equals
When I have time.
how many times is it?
One day.
I mean, it's Substitute x equals 0 into this equation. What's sine of x? Sine of 0. Sine of 0 is 0. 1 over 0. Infinity. Let's just assume that, right?
Yeah.
The answer is, yeah, of course. I want you to be confident about
The one that she sent it.
always have to.
I replied. I was like, thank you. Do I have a name? We're roasting her. Honest mistake, it's her.
Yeah, that's not.
But anyways,
I don't know, I consider, she called it study. From what I see, this is not.
This is what the later rates
And then change.
you just like find that on there, and it's
That's a dangerous way.
like you always find the page where it takes so
Okay, so let's work this out. We're gonna get so notice you can't even read the limit off of this because the limit as x goes to 0 of this guy from the right is positive infinity, from the left is negative infinity, right? So it's a hopeless limit to begin with. So what I recommend is you just sort of combine everything. So that's going to be limit x goes to 0 of what? So x minus sine of x over x sine x. Okay, so what happens if we put 0 into here? You get 0 minus 0, that's 0, and 0 times 0. So this is the indeterminate form 0 over 0, which means we can use L'Hopital's rule. We take limit of x goes to 0, and we're going to get, what's the derivative of the top? That's 1 minus cos of x. And the derivative of the bottom is, well, we got to use product rule, so we're going to get sine x plus x cos of x. So what happens if I put in 0 now? You get 1 minus 1, that's 0. It's not yet a problem. But then you get sine of 0, which is 0 plus 0. So we're still in an indeterminate form, but at least one that we can use L'Hopital's rule. Use L'Hopital's rule again. What do we get on the top? We get a 0 minus the derivative of cos of x, which is minus sine of x. So you get a positive sine of x over cos of x. And then product rule here, so you get cos of x minus x sine of x. So can we do this yet? Well, if we put 0 in, you get 0 on the top. That's not yet a problem. But on the bottom, you get 1 plus 1 minus 0. So that's actually fine. You're going to get 0 over 1 plus 1 minus 0, which is just going to end up being 0. Actually, I'm just going to write that in there and save me this space.
Professor?
Yes, sir.
You can only use the L'Hopital's rule if it's like 0 over 0.
Or infinity over infinity.
But you can't do it if it's infinity minus infinity.
No.
Okay.
Well, because 0 over 0, like, so remember when we're using limits, right? If we have a over b, we can always play tricks like 1 over a over 1 over b. Right, so 0 over 0, actually we can convert to 1 over 0, 1 over 0, which is infinity over infinity.
Yeah.
So those two cases are actually, they're not even different cases. L'Hopital's rule works in exactly one case, the 0 over 0 case. It just happens that we can get an infinity over infinity rule from the 0 over 0 rule. All right, so another one. New category. Indeterminate powers. All right, so first notice that according to the rules of limits, if we have the limit of x goes to a of ln of f of x is equal to L, right? Then the limit laws tell us that I can put all of this to the e. Right, so that means the limit of x goes to a of e ln f of x is equal to e to the L, which means that the limit of x goes to a of f of x is equal to e to the L. Right, so this basically is just noticing that we can bring things down off powers using lns, the same way we were doing in implicit differentiation. I'll show you how this works in an example. So again, I've just shown you a new tool, algebraic tool that you can use for taking limits now. That's why I'm not really talking about geometry or trying to make any associations. This is just something that's going to aid you with mechanically if you're trying to do limits and encounter something which is an indeterminate form. Okay, so I want to actually develop this rule. All right, so I read a rule because you don't have to remember it. But if you do remember it, it's going to save you a hell of a lot of time, because you don't have to rederive it every time. And the rule in this case is that the limit of x goes to 0 from the right of 1 plus x, 1 over x, is equal to something. Let's figure out what it's equal to. But when we figure it out, we should remember, so we don't have to do it every time. So let's try to work this out. Okay, so what I'm going to do for the time being is just say that this is equal to L, the limit. And we're going to try to work out what L is. So if that is equal to L, this means that the ln of L is equal to the limit of x goes to 0 from the right of 1 over x ln 1 plus x. Okay, and now let's work this out. What is 1 over x as 0 goes from the right? What's that limit? One of you must know, or I'm quitting. Right? This is 1 over x. This is 0 here in the middle. So what is 1 over x doing as we approach 0? Positive infinity, right? All right, so we get positive infinity multiplied by what? What is ln of 1 plus x as x goes to 0? Really, I'm asking you, what is ln of 1? 0, it's 0, yeah. I really should remember that ln of 1 is 0 and ln of e is 1. Okay, so is this, can I use L'Hopital's rule? No, because it's neither an infinity divided by infinity nor 0 over 0. Right, so the strategy here is just to move something to the denominator. Right, so what do you want to move to the denominator? Really, anything will do. Well, we can also do the other trick. Right, so the other trick was you let x equal to 1 over h. But what do we have to take h to in this case? Oh, hold on. I am being looking at the wrong thing. That's why I shouldn't read off this. My first thing was correct. We should move something to the denominator. Am I losing my mind? Yes, I am. Sorry, guys. This is why we shouldn't write things like this. I get confused. Let me rewrite this. All right, let's write this as ln 1 plus x over x. Right? Don't make the same mistake I just made. Right? You have to look at these things individually. Right? So as x goes to 0 on this, you get 0. And on the bottom, you get 0. So I did something very silly. Right? I took 1 over x as the thing. You're really just supposed to take the numerator and the denominator. Right? So maybe we should always strive to write things as a fraction, so that's very clear. I made the exact same mistake last night when I was working through this. Okay, so anyways, this is a little bit easier now. So this is 0 over 0, so can I now use it? L'Hopital. Yes. Okay, what's the derivative of the top? It's 1 over 1 plus x. It's 1 over what's inside.
Oh no, we're talking about.
I'm saying what's the derivative of ln 1 plus x? 1 over 1 plus x. That's the top. And what's the derivative of the bottom? Derivative of x. 1. So what happens if I run this limit? What do I get? Well, just substitute 0 in there and see what comes out. What happens when you put 0 in there for x? 1. 1's fine, right? Perfectly okay with 1. But what does this mean about L? Right, so we determined that ln of the limit is 1. So what does this mean L is? Look at the other board. When is ln of L 1? When L is equal to E, yes. So what did we just find out, actually? That the limit of x goes to 0 from the right of 1 plus x to 1 over x is E. Isn't that kind of neat? Anyway, it's worthwhile to remember this. Now, don't confuse E, this E, with E to the x. That's not what I'm saying that this is equal to. I'm saying that this is equal to E to the power of 1. Right, but I don't want to write E to the power of 1 because I don't want to strengthen the incorrect notion that we should treat E as anything different than a number. Because I would never write this is equal to 2 to the power of 1. I would just write 2. Right, so E is just the number. We just don't, well, we don't have a number for it. Okay, so that's a rule that you guys should remember. So let's try to do another one. While I wipe the board, you try it. I'll just write it here. Try to work out what the limit of x goes to infinity of x 1 over x. While I wipe down the boards, and then we'll do it. Everyone copy this board? All right. All right, do a lap. Give you guys a little bit extra time. This is actually the last example I have in the lecture, right? So then after this, I'm just going to give you like 10 questions to work out. Oddly enough, there are no Weeby work questions for L'Hopital's rule. Yay, you don't want to. I'm actually saying this because I'm disappointed. Like no one has programmed any L'Hopital. That's a bad attitude, right? You need to practice. So, huh? Oh, it takes. I'm not going to program them in. That would take me way too long. So what I'm going to do for L'Hopital's rule instead of giving you Weeby work problems is probably just give you a list of problems to work through, like on paper. I'll just post them to Quercus. But their non-appearance in Weeby work does not excuse you from having to practice them. It's just that I'm too lazy to program them into the Weeby work. It's funny because there's like thousands of problems on Weeby work.
Yeah, it stresses me out so much.
Well, that's not our intention, though.
Because I'm not
You can skip like a third of the question.
I know, but then once I finish a set, you upload a new set, so then I'm still a step behind.
This is a double-paced class, right? So if you wanted to do it slower, you should have done it through the year.
I like doing the Weeby work.
I think Weeby work is, whenever I've taught at other universities, normally it's the case that people say they like this type of Weeby
I
work
just like
stuff.
having unlimited attempts at doing it.
Yeah.
As opposed to being like,
Well, like that should remove the stress, right?
Last
There's
semester you
no,
had one try.
yeah, I'm giving you an infinite amount of tries. And some of the things I give you are like true-false questions, right? So they're not, like I'm not, like I really don't want you to be stressed about this. Like this is why we're trying to like ask you, you should be able to do 2 and 3 of the database without feeling stressed out. You shouldn't feel stressed about it. It's just practice. It's just practice. You should. You gotta have some. You gotta do some yoga or meditate a bit, right?
Practice on mine. Yeah, I got it. Yeah, L equals 1.
Because I don't want to make you stressed. It like makes me sad that you're stressed.
The stupid part is they make you do all this math, and then, for example, in my program, I don't ever have to take math again.
But it's not about like this is a vehicle for teaching you critical thinking, right? Like you're not going to do critical thinking into the future. Right? Like, this is going to be useful for you for a variety of reasons. Like you don't study Shakespeare to be an expert at Shakespeare. Like we study it to understand like themes that are present in history, how to write, right? So you may not have to use calculus, but you're certainly going to use these skills of like abstraction and like problem solving. Right? So that your employers don't necessarily want you to be able to take integrals. They just want to be able to be assured that you can understand something like this is not real. Like mathematics isn't like really real. I can't hand it to you. It's purely like imagined by humans. Right? So you're proving to an employer that you're capable of understanding something that's like an imagination machine rather than like a car or something like that. The ability to abstract is quite important. That's why people don't like math. Right? It's not like you don't like calculus. It's that like critical thinking and abstraction is something difficult. It makes us uncomfortable. Right? We're humans. We prefer to have something to hold on to and look at. And like I take that all away
That's
from
me,
you.
that's why I like science, because I like being able to observe something and analyze it.
Yeah, okay, but like so let's see how you're going to do now when so optimization is the next topic. And that's basically that's science. That's science, right? So so we'll see how much you like. So this really science is the taking English to math. That's what I would say science is, right? So you should be an expert at these word problems, right? The mathematicians don't have to care about the word problems because they only care about the like math itself. Like they'll talk deeply about proofs and limits and like the epsilon delta. We don't really care about the word problems, right? But scientists, you have to take problems of the world that are like not really well defined, and like you give them good definition. Like even to take a problem and to say, this is what I want to extract from it, you'll need math.
My goal is to be isolated in a laboratory in Alaska and have to research the world while I study some genetic virus. That's what I, yeah. I don't know, I hope it's so cool.
So like that, what's that movie with the blob?
The blob?
Yeah, like the thing.
All right, see most of you on your phone, so let's just work this guy out. So here's, we're going to develop a rule. So this rule is going to be limit of x goes to infinity of x 1 over x. Does anyone know what this works out to, or have any of you worked this out? Any of you remember what this should be?
Set it equal to.
Okay, well, yeah, I just want to know if anyone knows the answer ahead of time. Yeah?
I got 1.
You got one? You got one? Who else got one? Good, it's 1. Okay, let's work it out. Okay, so we're just going to let this equal to L, which means that the logarithm of L is equal to the limit of x goes to infinity of 1 over x ln of x. Right, so let's not make the same mistake again. So if I run x to infinity, that means the bottom is going to go to infinity, and the top is going to go to what?
Infinity.
Infinity as well. So that is actually a form we're allowed to use L'Hopital's rule for. So let's take L'Hopital's rule. So derivative of the top is what? 1 over x. Derivative of the bottom is 1. I can take
That's it.
x to infinity, so that means I'm going to get a 0 over 1, which is 0, which means that ln of L, the limit we want to find, is 0, which means L has to be 1. Right, so that's how you get this. So it's also handy to remember this limit. That is x goes to infinity of x to 1 over x, that goes to 1. Okay, so that's basically the end of like the instruction part. I'm going to give you a lot of problems to do now.
Yeah.
So talk, move around, get coffee. Instruction is over.
So remember when you set it equal to L, what you do to both sides is that you put an L on L, and then on X, and then you bring the 1 over X to the front. These are basic. Yeah, the reason we put L is so that we're able to get the volume of L. It's just a